Hey guys, welcome to section 13.1. We're starting a unit on counting and probability. So 13.1 is about counting, and it starts with finding all the subsets of a set. So let's say you guys have a set containing the elements A, B, and C, and we want to find all the different subsets of this set. Okay, so there can be subsets with 0 elements. There can be subsets consisting of 1 element, and there could be subsets consisting of 2 of the elements, and there can be subsets consisting of 3 of the elements. So the point of this first one is to write down all of these subsets. So if there's 0 elements, then that's just the empty set. So that's the symbol. If there's 1 element, let's see, it could either just be subset A, B, or C. So there's 3 with 1 element in it. Now all the ways that we can write a subset containing 2 of the elements, so this could be A and B, it could be A and C, or it can be B and C. So those are the ways that you can write 2 elements in a subset. And then a way to write 3 elements in the subset, there's only one way, the one that contains all A, B, and C. All right, so how many are there total? 1, 2, 3, 4, 5, 6, 7. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So there's going to be 8 total subsets. The empty set, these, and these. And it turns out, here's a formula for it. If you have a set A with n elements, there's going to be 2 to the n power subsets. So if we have 3 elements, 2 to the 3rd power is 8. All right, so now let's look at a Venn diagram example. It says, in a survey of 100 college students, 35 were registered in college algebra. And you know what, guys? I'm going to actually keep this, but I'm going to do it another way also, just in case this way makes more sense. So let's do, we'll call this college algebra and then computer science. And in this example, this is college algebra and computer science. Okay, so in my example, 35 were registered in college algebra. So this whole circle is going to have 35, and then 52 were registered in computer science, so computer science circle gets 52. And then it says 18 were registered in both, so we got the 18 in the middle. And then this is how they got this picture. If we just subtract 35 minus 18, that tells us that 17 were only enrolled in college algebra. And then 52 minus 18 would be 34 enrolled only in computer science. So I just wanted to show you guys where they got these numbers from. That's how they did it. And then you can use either one of these to answer the questions. So like part A says, how many students were registered in college algebra or computer science? So there's a couple ways to do it. You could do, so here, this is part A, college algebra or computer science. So you could do college algebra only plus computer science only plus the 18 that were registered in both. Okay, so again, one way to do A, it's the 17 for the college algebra, the 34 for the computer science, and then the 18 that are in both. And if you add those up together, you get 69 students. Another way you guys could have done that is 35 plus 52, but then subtract out the double counted 18. So I'll write that down too. You could have done 35 plus 52 minus the 18. That's another way that you could have got 69. All right, lots of options in the probability chapter. All right, let's look at B. B says, how many were registered in neither course? Okay, and let's note that there was 100 students total. So if there was 69 registered in either college algebra or computer science, then just 100 minus that would be registered in neither. So all we have to do is 100 minus the 69, and that gets us 31. All right, so that's how to use a Venn diagram to answer questions. And then here's a big formula here. If you guys don't know the notation, this is called union, this U, and that represents like a total. And then n sub A, n sub B, minus, and then this upside down U is called the intersection. And that's like where they both contain elements, like they're intersected, both. And then another important thing that I think helps, when you're talking about the union total, think of or, because they want this or this, which is like the total. And then when you're seeing intersection or both, think of that more as representing and, because they have to contain both. That's the intersection. Okay, so this is a good formula. If you want to find the union or total, the or, you add A plus add B minus the intersection. If you want to go back to this one here, this formula, technically we used right here. We did how many in college algebra plus how many in computer science minus the intersection. Okay, so this formula we kind of already used. Okay, let's move on to some cards. So I don't know if you guys are familiar with playing cards, but there's 13 of each suit. So 13 clubs, 13 diamonds, 13 hearts, and 13 spades. All right, and it goes from ace through the face cards of king. So the probability of getting a king, if you notice, there are only 4 kings out of 52 total cards. So the probability of getting a king is 4 out of 52. And if you want to reduce that, it would be 1 out of 13. All right, the next one says, what's the probability of getting a king and a red? All right, so pretty much, what's the probability of getting a red king? So now if you look at the kings, only the, see, and I don't know how well you guys know cards, only the diamonds and the hearts are red. So therefore, this whole row is red and this whole row is red. So there's only 2 red kings out of all 52. So this would be 2 out of 52, which reduces to 1 out of 26. All right, now this one's saying, what's the probability that you get a king or a red? And here's where I might go back up and use this formula now. When you want the or, king or red, you do the number of kings plus the number of reds minus the number of red kings, right? Because you don't want to double count those. So one way to do this is use that formula. So the number of kings would be 4, right? 4 kings. The number of reds would be 26 because we have 13 red hearts and 13 red diamonds, so 26. But then we're going to subtract the intersection of the red kings, and there are 2 of those. All right, and again, that's all out of 52. So if you work that out, what's that? 30 minus 2 is 28 out of 52. And that reduces to, let's see, by 4, 7 out of 13. And then here's a new symbol that you guys might not know. This means given. So what is the probability that you pick a king given that you know it's a face card? So now our denominator is going to change. We're not talking about all the cards. We're only talking about if you know it's a face card. So if you know it's one of these, what is the probability that it's a king? So our new denominator now is 12. What's the probability that you get a king? 1, 2, 3, 4 chances out of those 12. So the probability is 1/3. All right, so just a little bit with cards. And then the next page is where? Oh, over here. Really easy, just the counting principle. Okay, so counting the number of possible meals. You guys are going to love these. Let's say you have 2 choices for an appetizer. 1, 2, 3. 4 choices for an entree. 2 choices for a dessert. How many different meals can be ordered? Okay, so we have them here. 2 appetizers, 4 entrees, 2 desserts. How many different meal combinations can be ordered? Well, one way to do it is to make a tree diagram. So we'll have the appetizers, and then from each appetizer stems out the 4 entrees. And from each appetizer entree, we have stems the 2 desserts. And if you tally up all the end lines here, it ends up being 16. But a lot of people don't want to make a tree diagram every time. So the multiplication counting principle says if there's P selections for the first choice and Q selections for the second choice and R selections for the third choice, the task of making these selections can be done in P times Q times R, and then if there was more, just keep going. So basically 2 times 4 times 2, that's another way to get 16. All right, so let's try one of those. Forming codes. How many 2-symbol code words can be formed? So I'm going to make 2 things here. I'm not going to use the tree diagram. If the first symbol is an uppercase letter and the second symbol is a digit number. Okay, so how many different ways can you make a uppercase letter? So how many letters are in the alphabet? That's 26. And then times, right? Multiplication principle says times. How many digits are there? So can't digits be like 0 through 9, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's actually 10 different options for a digit. And if you multiply those, that would be 260 code words. All right, that's it, guys. That's 13.1. Thanks for watching.